we're going to start by giving people sort of an overview of what the issue is of nuclear power and fusion power. I'm sure you've noticed that Arush has been very emphatic about how we have to get the entire world economy focused on making the breakthrough into fusion power. And what we want to do is sort of give you, well, go back here. Actually, what I was going to do is, let's see here. All right, well, I'll just go through this. The issue is, this is, it's been a fundamental fight since the concept of fusion as a concept goes back to Einstein. So it's been over 100 years that we've had some concept of fusion power or nuclear physics that could actually generate power. And it's awesome the amount of power that we could generate. Can anybody identify what this is? Besides the obvious?
Well, it's the sun.
Yes.
Showing nuclear actions going on, and then the Earth. I guess that little
the little spot there
would
is
be our
the size of the Earth. I don't know if that's exactly a picture, but
Sure not. It has to be far away than that.
the third planet from the
well,
sun.
it could be shining. It could be a camera looking through the sun's atmosphere to the
Is that
Earth.
like what is that?
That's a solar prominence.
Prominence.
A prominence.
Yeah. Now the point I was going to make was that this is a gigantic fusion reaction going on. And within the center of the sun, the temperatures are between 30 and 40 million degrees. And that's what enables this fusion process to occur. And then, oops. Yeah, this one here. Can anybody tell me what's going on here?
Milky Way.
Well, it's not the Milky Way. That's another galaxy.
Yeah, that's another.
However, what's going on? What you're seeing there are, billions and billions of fusion reactions powering all these spots of light and blobs of light that you see.
Stars.
Now, the spots that you see that are apparently closer are stars within our own galaxy. That we're looking through the galaxy out to another galaxy. Now, okay, whoops, keep skipping this thing. This is just very interesting because it just shows you what mankind has actually been able to do. This is a picture of Saturn. It's kind of obvious that's what that is, right? Right? And what they've done, this is a picture taken from the back side of Saturn, the night side. The sun is on the other side, so you're seeing the sunlight coming through the rings and things like that. And NASA has identified where various objects are. These are all the moons of Saturn. That's where the Earth would be, if you could see it. It would be very small from this perspective. And that's where Mars would be. And that's Saturn, and the sun is on the other side. So here's an example of human beings developing the capability to send a spacecraft out 1 billion miles to Saturn, and then take a picture and look back at where we are. So we're looking at ourselves right there. Pretty neat, huh?
Yeah.
This is a completely thorough, let me see if I can
Zoom in.
I don't know.
What's zoomed in this picture?
Yeah, okay, that's about as good. This is a chart of something called the electromagnetic spectrum, which is all of the wavelengths of energy that we know about, right? This was put together by Westinghouse Corporation some time ago. But it goes all the way from radio waves and the level of sound waves down here, which you can hear, up through infrared heat, that is infrared radiation. Visible light is only this little sliver of the spectrum. That's all we can see. And the entire amount of energy in the universe, all we can see is in this little tiny sliver where the wavelengths of light are, right? Ultraviolet, X-rays, gamma rays. And what Howard's going to go through in some detail is what this has to do with the structure of the atom, right, and how we actually use this. This is a picture of the whole periodic table of the elements. You know, all the elements that we know of, and elements that have been just created in the laboratory. Way down here, this is uranium. Plutonium is over here. Thorium. You know, the ordinary elements everybody knows about, from hydrogen, helium, you know, iron, copper here, silver, gold, you know, all the basic elements, right? And they all are defined by having a different number of protons and neutrons in them, which define how heavy they are and things like that. This is a description of what happens in a fission reaction, which is what our atomic power plants are now, is fission using uranium. The uranium atom is hit by a high-speed neutron, and it splits and creates two other elements, which are lighter elements, and it releases a couple of neutrons and a tremendous amount of energy. If you have a continuous process going on like that, it's called a chain reaction. And if it's inside of a nuclear power plant, you have a continuous source of heat, which is what keeps the thing going, so you can generate electricity. If it's an uncontrolled chain reaction, you've got the old atom bomb, right, which is quite destructive. And on the other hand, we have something called, oh, by the way, I'll just make a point, that the fission reaction takes place with the heaviest elements, like uranium. They're heavy because they got a tremendous number of protons and neutrons within the core of the atom. And the lightest element is hydrogen, which is the most abundant element in the universe. It's hydrogen, and it's basically one proton and an electron that goes around it. Now the proton is positively charged, the electron is negatively charged. This is a picture of what happens in a fusion reaction, like what goes on inside the sun. However, you'll notice that this is a blue is the neutron and the yellow is the proton. This is hydrogen, but it's got an extra element. The extra neutron is called deuterium. And this is called tritium, which has got 3 parts, 2 neutrons plus the proton. When they get forced together, they create, the byproduct is helium, which has 4 elements. You can see you get 1, 2, 3, 4, 5, and they come together. You get the helium with 4, 2 protons and 2 neutrons, and you get 1 neutron flying off, and there's a tremendous release of energy. This picture goes through what that energy is. If this is the if deuterium has 2 particles, so it's it has a mass of 2, and the tritium is a mass of 3 because it's got 3 particles in it. If they come together, you would think the combination would be 5, but it turns out it's a little bit less than 5. It's 4.98, and then 1 neutron flying off. However, the 4.98 and the energy, what that represents is this equation that Einstein made famous, where the energy equals the mass times the speed of light squared. That's what the c squared represents, right? I'm not going to explain what that means, but the point about it is that you're converting a portion of the mass into energy in this reaction. And it turns out it's a whole lot of energy. If 1 unit of energy is equal to the energy used by 1 US citizen in 1 year, that's 1 unit. This reaction releases 676 units of energy. So that reaction releases that 676 times the amount of energy that may have existed prior to that. So it's a huge amount of energy. And
one atom,
this is just describing one fusion reaction.
676 units.
Units. Well, if 1 unit of energy equals the amount of energy used by 1 citizen in 1 year, how many kilowatts of energy that is, I'm not going to estimate. That's how many more times power comes out of it. You just have to think about, you don't need to focus on the numbers, but it's just think about the scale of transition that's going on here. That's what it means when you say mass is converted into energy. And, you know, again, I'm not going to try to explain a lot of the technical details of what this is, but that is what occurs. I mean, after all the stars, our sun, all work on this principle. Fusion energy does do this, right? This is what happens. We're here because of that. We were born out of the sun. You know, the sun created the planets in the solar system and everything on the life on Earth. So out of this fusion reaction came everything that we know of, in a sense, you know. This is just another little illustration. And this, what happens is in the sun, you've got a situation where you've got a tremendous amount of pressure and temperature because you've got a huge amount of, the sun is quite huge. So the gravitational forces compress all this gas and it can create the fusion process. Now on Earth, human beings have to figure out another way to do this. Since we don't have the massive mass of the sun and the ability to have that kind of pressure, we have to do it within something different. One of the ways that they've worked on is called a magnetic confinement, where they use gigantic magnetic fields to compress this hot gas, and the gas is called a plasma because it's ionized. It means the electrons have been separated from the regular atoms. And I'm going to demonstrate this in just a minute. I have this extremely dangerous scientific laboratory setup here. I want you to just, don't be afraid. Nobody's going to die. We're going to demonstrate how a plasma works, okay? I have clearance from the DOE. And the other way that they do it is with tremendously powerful laser beams. And the laser beams are focused on a little tiny pellet of the fusion fuel. And the pellets are quite small. This is, well, the magnetic confinement is, the big project that we're working on in Europe is an international project. This is called the International Thermonuclear Experimental Reaction, or ITER. And you can see the size of it. That's a laboratory worker right there.
Wow.
It's gigantic, right? So you can compress this plasma inside this donut-shaped containment place where all this magnetic field is surrounding it and compressing all this gas. You're going to get some potent reactions going on. And they intend to create a proof of principle that you could actually run a power plant by doing this. And this is a guy working inside of it right there. This is not the same one, but it's a similar one. Right? He's not going to stay there, obviously. So, this is the pellet that's used, or an example of the pellet used in the laser fusion, like the Lawrence Livermore National Ignition Facility, they call it, uses a pellet that looks like this inside this gigantic chamber with all these laser beams coming in from every direction. And it hits it all at once in a split second, creates tremendous heat and pressure on that pellet, and it creates enough pressure to cause that fusion reaction to occur.
Is that made of one of those elements you were talking about?
Well,
Material?
within it, I don't know what's coating it. There's something coating it, probably maybe gold or something like that. But within it is the deuterium and tritium in some combination. I'm not quite sure how they do it. And how they put it together, it's extremely delicate, so you got to get the right combination in there. This is just an example here of the fact that this goes back to this issue of what Kennedy would have done. Had Kennedy not been killed, if we still had the Kennedy momentum going on in terms of the science and the economy. And by the way, I don't know if, everybody except for Howard and Daniel were probably alive when Kennedy was killed, right?
I guess.
Yeah. I mean, they weren't born yet.
Let me take a look at everybody. Yeah, that's true.
Okay, the point I'm making was this, that I remember when I was 11 years old, the thing I feared most is that we wouldn't continue the space program. Well, unfortunately, my fears have been confirmed, you know? Well, this is the same thing. We had all these, beginning to get breakthroughs in the scientific laboratories in the 70s. We had fought like hell to get a bill passed by the Congress in 1980, which did get passed, the McCormick Fusion Engineering Act of 1980, to mandate a level of funding would actually have gotten us to the point of having a commercial fusion reactor working by the end of the century, by the 1990s. There was other levels of funding that could have done it a little bit later. We would have already had it, either way. But at the level of funding we have right now, we will never get it. And it's like if you were trying to have if you had a speed limit on the runway at the airport, and you couldn't go faster than 60 miles an hour, you'd never get airborne, right? So that was deliberate. Now this is an example of a historical archaeological research that's been discovered. This was on one of the cave paintings, I think. Now, I'm going to demonstrate this scientific research here, because obviously our ancestors.
Are we gonna be safe?
We're going to be safe. Our ancestors obviously did some experimenting, and they figured out how they could actually. They probably saw that it was useful to have fire because they could cook their food and things like this. And I'm not going to get into figuring out how that first occurred, what may have happened. But anyway, the point is that this is, mankind is the species that actually discovers things. We figure out how things work. We think about what the future situation will be and act accordingly. We can actually decide, well, if I rub these sticks together, I'm going to get more heat. If I keep doing it, I might get a spark. And you'd have to be able to figure out that that's what would happen. Now, no animal would ever do that, So, I'm gonna skip over this for a second. This is just a historical picture. But let me go to my scientific. My assistant can help me here. And you see, this is extremely sophisticated, high technology, and you don't need that. I will need this. Now, the cavemen didn't have this either. So we have some advantages. All right, now, what I'm going to do is, first of all, light this thing up. This is just to keep it from falling over, do anything bad. Now what I have here is a regular old 9-volt battery. It's actually been run down a bit. I'll just demonstrate. This is a multimeter which shows you how much voltage, for example, you're going to get if you touch the So I'm going to touch the battery terminals with this thing here. Oops. What's it say?
It reads
5.6.
5.6 volts.
All right. Maybe it's a 6-volt battery. All right, so it's a live battery. There's yeah. Right. What I'm going to do now is, obviously, if I just hold these wires close together, they don't do anything, do they? However, what happens now?
A 0.003 hundredths of a volt.
Yeah, we can turn it down to this lower setting. Oops.
.001, 01.
A tenth of a volt.
Mhm.
Yeah, okay.
But it goes up when you put it in.
Yeah, in other words, there is a, in other words, the current gets transmitted through the flame. What's happening inside the flame is that some of the air, some of the particles within the candle are getting ionized because of the heat. Not a lot, but it does ionize it, which means that there's free electrons being
Yeah.
liberated from the atoms in
Neutron activity.
in the flame. So the electrons can transmit the electricity. It goes through the whole circuit, right?
Mhm.
Now, if I, here it is. This is what
Maybe you could move the box in the.
oh, yeah. Here's what I wanted to do, is actually do it this way. So we get the power of the battery showing. Oops. There we go. And then. Oops.
Oh, just keep leaning back. I can't see. Thank you.
Now let's see what happens here.
Mhm.
Yeah, do it that way.
Yeah. Um,
15, 17.
0.1 volts, 0.2.
That's going down to 0, right?
Mm-hmm. It's at 0 right now. And the wires are in the flame. It's about 0.1, 0.2.
Okay. You turn it down to the lower setting just to give you a sense of something more dramatic.
Can everyone see this? Mm-hmm.
Yeah, so it's, what is that, 2/10 of a
Mm-hmm.
volt? Yeah. Anyway, the point I'm making is kind of obvious. Now you have a situation where within the flame, the current is transmitted all the way through the circuit, from the battery through this thing and back. And that's because this flame is a plasma. And that's what our ancient ancestors were actually figuring out.
And
Doing
just,
plasma physics.
Just to use the chorus principle from Henry V. If you take a really strong magnet and you place it near the flame, the magnetic field actually shapes, the flame actually is shaped by the magnet. And all the fusion reactors is a giant, really big candle and really big magnets channeling this plasma into a very dense, hot plasma to where it actually reaches fusionable.
Why don't you go ahead with your
Okay.
side.
Right. My presentation.
Turn it on. Gotta get out of the way.
All right. I know Art mentioned the uranium fission and the hydrogen fusion, but there's a very, and you know, the periodic table has, you know, around 100, 110 known elements. I think they actually recently discovered a new one a couple of weeks ago. I don't know the name of it.
About 115 or something.
Mhm. But there's another way you can actually look at these elements or atoms. You can actually, there's many, many more than the 115 that we know about. And my presentation is on, you know, those many, many more atoms. We call them isotopes. And this is a picture of the sun. We just went through that, how you have different isotopes of hydrogen. They said they were deuterium and tritium, fusing together to create helium and energy. But back in, well, let me get my notes actually.
He discovered the levels of J.J. Thompson.
Mm-hmm.
I think it was 1871.
Mm-hmm. Yeah, J.J. Thompson. In 1913, he was actually, he's a British scientist. He was actually imprisoned in a detainment camp in World War I. There's a lot of the Allies that were living, studying, or whatsoever in Germany when the war broke out. Scientists, whatever, where they were detained during the course of the war, and they were actually treated very nicely. These were not the detainment camps that 20 years later, you know, that happened. But he was experimenting with ions and different of these atoms and gases and so forth. And many of you have, and I'll skip, many of you have heard of a cathode ray tube, I imagine. The old bulky TVs had the vacuum tube in the back, and they had the, what that is, and I'll go through this. You have a long glass tube, you know, shaped like this, and you have a cathode and an anode connected at the end. A cathode is like a metal plate, and same thing with an anode. The cathode is where the negative charge is stored, and the anode is where the positive, you know, in a current. And so what J.J. Thompson didn't do this, but I just want to illustrate the principle that you take an electric, or the negative charge cathode over here, and you have the positively charged anode, and you run a strong current through it, through this, those two things. And what happens with the rest of the glass tube is that you had a ray shoot across, called a cathode ray. And at first, they didn't know what it was. That actually, it happens is because, well, we know now that the electrons from the negatively charged cathode are attracted to the positively charged anode, but they move so fast that they just shoot right through. I guess I should say the anode has a circle, a hole in the middle of it for the electrons to go through. And so they went to the other side, and they had a little photogenic plate that the electrons would hit, and it would discolor. And so at first it was just this ray of light. They didn't know what it was. And so they just tried a couple of things, like having another one of these plates with a positive and negative charge. And then they realized, and they hooked up the current again. And the ray going through this plate bent down. In this picture, it bent down. Which means that whatever this cathode ray is, it must have some sort of negative charge. Because you know, negative and negative repel, and negative and positive attract. And so you had the negative on top, and the ray bent down. And they also did the same experiments with magnets, and it did a similar thing. Now that's a cathode ray tube, and that led to the discovery of electrons. J.J. Thompson did an experiment with a little bit of a different setup called an anode ray tube, where the plates are actually switched. And I have a better illustration. This is actually a replica of one of the instruments he might have used back in 1913. But what he did is that this is a modern one. This is an anode ray tube, and that's the anode part of the plate, and I believe that's the cathode. So they're switched, and so you also ran a current through there with the neon gas within the tube. And what had happened was you had another ray flying through the tube. In this case, you can see that's the neon ion being thrown up. And it also had a discoloration of a photogenic plate on the top end that would discolor. And he did the similar experiments with the electrical plates and magnets, and it also deflected. But this time, if you think of it, this is now the negative, and this is the positive. The ray bent downwards away from the positive. So whatever beam was being shot through had some sort of a positive character to it. And this was the neon ions. And so this is a picture of, I think, the actual plate that he used and this is the center of the tube. These are some deflections and so forth. And this is the neon down here at the bottom. NE is for neon. But what had happened is that you had two different markings on the plate, on the photogenic plate, because they thought it was just neon. They didn't know of any other varieties. But you had these two markings at the bottom, and so what that would indicate is that with, if there's two different kinds of neons, because they're deflected by this electrical or magnetic current in the tube. And I'll go back to it. One neon, of course, went like that. Another neon went a little bit more. So perhaps the second neon atom had was either heavier or had a stronger charge that propelled it more. It was a stronger repulsion from the plates. But it was eventually figured out that it was heavier. There was more mass with the second neon than the first. As you can see, it was deflected. It's a tiny deflection, but it was enough to actually bring up this discovery. And that is, how we figured out that there are isotopes. That there are elements. The normal elements have different variations to them. And I'll get to how many they are. Okay, this is a second scientist, William Draper Harkins. He was looking at spectrographs. Essentially, every element has its own unique radiation. And this is just an illustration of a prism. You take a white light through a prism, and it separates into its the red, yellow, orange, green, blue, purple. The white light is separated. But each element has its own sort of separation. It doesn't always separate into the full rainbow. It has different lines to it, different colors that it separates into. The first one is hydrogen. If you burn a hydrogen flame, you notice that it's red. It's light red color with probably a little bit of a bluish hint to it to get a little bit more purple. And that's because the emission of a hydrogen atom is that color. That's what the frequencies are. And the bottom one is iron, for instance. Molten iron, is stages from red to orange to yellow, then eventually white and so forth. That's the emission of an iron atom. But what William Harkins noticed, that the same atoms, so-called beforehand, would have slightly, take neon or hydrogen or so forth, for example, that different atoms would have very slightly different spectral lines. And so there must have been very, very slight. And so his hypothesis is that there could have been another characteristic. And I think he knew about isotopes, I guess I should say. He knew about the change in weight. But he was hypothesizing with this experiment that there's a little bit more to an isotope than just the weight. You know, just the different weights between the atoms. That somehow, because I should explain, it's the electrons and the energy of the electrons in the outside of an atom that give off light, for instance. If you shoot an energy at a certain, say iron for instance, some of its electrons will absorb that energy and go to a higher state of energy. And when you stop shining the energy at the atom, the electrons fall back to a lower state and they release that energy as the form of either visible light or whatever other type of light. But people had known, Harkins had known that, okay, the isotope, you know, the difference is in the nucleus, so-called, with the protons and neutrons. I'll just say that an isotope has, the protons are the same, but the neutrons are different. And I'll go back to, you know, neon 20 is the normal neon with, neon has what, 10 or 11 protons? Okay, whatever. 10 or 11 protons and the rest maybe 10 or 9 neutrons. But neon 22 has the 10 or 11 protons, but an extra 2 neutrons. There are 2 more neutrons in the nucleus than in the neon 20. Now a neutron and a proton are relatively the same mass, but protons and neutrons are much, much thousands of times heavier than an electron. And so the difference is, you know, they know that the difference between the isotopes is weight. You know, 2 more neutrons adds, you know, however slight, but there is a weight difference. Okay, it's 10 protons for neon. But Harkin's experiment with the different electron spectrums, which is the outside of the nucleus, hypothesized that there's more to these isotopes than just 1 extra neutron. And I won't get into the specifics or the physics of the nucleus, how it might be shaped, but that he hypothesized that the shape of the nucleus is actually, it's related to the whole atom. You don't just have an electron in the nucleus. You know, electron, you know, the general picture, you have the nucleus and you have the electrons around in some sort of orbits. But he hypothesized that there actually might be some relationship between the whole of the atom. But I won't get into specifics there. This is just to show that a neon atom with the normal neon 20 has 10 neutrons and so forth in that configuration, but a neon 22, an additional 2 neutrons, has, you can see there's more neutrons in the nucleus. And there's over 3,000 known isotopes. There's 115 elements, but most of those elements have from, some only have 1. I think there's a couple that only have 1, but some have 10 or more different isotopes. Most of them very, very radioactive. If you created, I think, say neon 30 or something like that, with an additional 10 neutrons, it would decay really, really quickly. It would be so unstable that you could not use it for any practical purpose. But there are a lot of isotopes that are stable, and there are a lot of isotopes that are radioactive. That means they are slightly unstable and decay. That's just a picture of a chart of all the isotopes. There's a lot of them. And most people have a first-hand experience of some of these radioactive isotopes in the medical field. I'll just go through that a little bit. You know, I think nuclear fission, which is the uranium split it off was hypothesized, I guess, by Einstein, but I don't think it was actually fully observed until 1939. And it was 1945 that the actual atom bomb was produced and used. So people know the Manhattan Project. And within a very short couple of years, they took the theory and the observation of nuclear fission, and they used it for, you know, the nuclear bomb that we know of, the Hiroshima and Nagasaki. And so, in the 1950s, some of these radioactive isotopes were being, you know, looked at into, you know, the medical field, especially with, you know, most people know of cancer treatment and so forth. The first one in the early 1950s, iodine 131, is a radioactive isotope. The thyroid in your neck intakes iodine at a certain concentration. And so this radioactive iodine 131 is it's uptake into your thyroid, and a cancer cell, which is a very fast growing, if it's malignant, intakes this really, really quickly. And so one of the things you can do with knowing that the cancerous cells intake this radioactive iodine really, really quickly is that, you know, these radioactive isotopes decay and they emit radiation. And if you have a scanner like that, you can actually take a picture of where that radiation is coming from. I don't know if I have an example. No. Let's see. And it's one of the uses to actually locate where some of these cancerous cells are. There are, you know, numerous terms of different isotopes. I have a couple. Fluorine 18, which is a radioactive isotope. You know, you can locate melanoma, thyroid, pancreatic, prostate, a whole bunch of these different cancers. Gallium 68 for breast cancer. You know, a whole bunch of these various atoms and so forth that we know the isotopes, which are radioactive. Over the, you know, the next several decades, we've understood which organs, which cancer cells, which tissues, which chemical, biological processes, which of the radioactive isotopes they intake. You know, iron, an isotope of iron, iron 52, because iron is used in the blood, in the hemoglobin, you can actually start to look at anemia, for instance, where some of these, where the red blood cells go wrong. Why is the hemoglobin, which is a protein that carries oxygen to your cells, in people who are anemic, that hemoglobin is slightly deformed, I would say, because of some genetic in the DNA that creates the protein. You know, you can have this radioactive iron 52, and I don't know exactly how they actually use this, but I can guess that the deformed hemoglobin, you know, takes this, and you can trace it back to maybe where the red blood cells are formed, and maybe it's a specific part. You know, red blood cells are actually created in your bones, in the bone marrow. There's a cancer in your bone marrow that are creating these anemic cells, and you can trace back. That's one example. And you have, you know, hundreds of these different isotopes for various cancers and so forth. The most common one, and there's a couple of reasons for why it's most common, is Technetium 99. It's one of these elements that no one ever hears of, you know, in the middle of the periodic table. It's about 80% of all medical diagnostics for radiation, these isotopes, is this technetium. There's a couple reasons why. It has a medium half-life, meaning it decays not too quickly and not too long. So it remains radioactive long enough for you to inject it into a patient, so it could be absorbed into the cancer cell and you can scan it and so forth. But it's not too long that it stays in your body and actually causes you to have more cancer. That's one of the main things. It's actually it's developed in nuclear power plants. So it's another reason why we need these nuclear power plants and these breeder reactors. Let's see what else. Oh, this one's actually pretty interesting. Very cool. It's called neutron capture theory. Theory. This relatively stable boron-10, it's non-radioactive. But what they do is that boron-10 is injected into, it's used for like brain cancer. I guess they inject it into various parts in the brain, and brain cancer cells intake this really rapidly. But it's stable, so it's, okay, so what's the point? But this picture right here, this is the patient. This is actually, this type of diagnostic is only used in power plants, because you have to have the type of radiation that's a bunch of high-speed neutrons can only be formed in a nuclear power plant, at least so far. And so what they do is that they actually shoot these high-speed neutrons, very targetedly, very precise, into where they know that the brain cancer is, and so that's what you see on the top right. And what happens, because these cancerous cells have this boron-10, you have this very targeted neutron laser that actually hits the boron-10, and it actually transmutates, it changes into boron-11. You add a neutron. And that's a very unstable radioisotope, and so it almost instantly decays. And what it decays into is an alpha particle. An alpha particle is essentially a helium nucleus. It's a form of radiation. It has 2 protons and 2 neutrons. It's fairly energetic, but it doesn't travel very far. Like your skin will block an alpha particle radiation, but this is within the cancer cell. So what happens is that this alpha particle, destroys the cancer cell from within. It also releases a gamma ray, but that's not, it doesn't actually harm the rest of the brain tissue. So it's a very targeted use of these isotopes. And I think it's still experimental as far as I know.
So they just do experiments in nuclear power plants?
Yes, I think so.
They don't actually treat anybody.
Mm-hmm.
What did you say about technetium?
It's 80% of the nuclear diagnostics for PET scans is this technetium, which is just an isotope of technetium. And this is a picture of a PET scan. Some of you might have had this, where you have these hot spots, so forth, with various, not just cancer cells, but any normal organs, say. This looks like maybe the pancreas or maybe the liver. Various organs, they uptake various isotopes more than other organs, and so you can actually have a picture of these organs and some of their internal structure, and if it's a cancer cell, you know that it uptakes very quickly, and so you can find out by scanning the area where the cancer is. And now that you know where it is, you don't have to have sort of a generalized either chemotherapy or radiation therapy, that's sort of just general radiation onto the affected organ, you know where the actual cancer cell is. And this is, of course, this is improving every couple of years. The technology is getting better. So that's that. Okay. And so this is the political part of the presentation, because these isotopes that are very crucial, they're necessary for some of these medical diagnostics and treatments. They're produced at nuclear power plants and nuclear breeder plants. This is actually the Hanford. This is actually called the Fast Flux Test Facility in Hanford, Washington. This was actually one of the breeder reactors that John F. Kennedy set up, or that he announced. I think it was actually in September of '63 that he made a speech opening this breeder reactor. He didn't, I guess, he didn't live long to see it finished, but it was it was the largest producer of these radioactive isotopes. I think it was actually I'll just read a quote. How much actual of these isotopes are neutrons as well to create the isotopes? There's about 7.5 times 10 to the 15 neutrons per square centimeter per second. That was the production rate of this research. It's about 750 times as fast or as much as other research reactors. So this is a very high density isotope generator, essentially. This was actually taken down in the early 90s. It was taken down.
So it's not functioning anymore.
It was stopped in the early 1990s, and it was eventually decommissioned in, I think, 2005. And there was a big fight to save it, I guess led by us as well, but that was not one. And this is the same picture that Art showed you with the takedown of the funding for fusion. It's a very similar thing for nuclear power. I think I actually have.
So where did they get these isotopes now?
There are other facilities in Canada and Japan. Other nations that have these breeder reactors. India just announced it was building its. It was building a new reactor. Here we go. Yeah, they're building a 500 megawatt prototype fast breeder reactor. They're constructing it now, and it's proposed to be built by 2020. But you have a couple of these reactors in Japan, in Europe, in Russia, in Canada, but we don't have one, at least of the type that the Hanford site was. So we import all of our radioactive isotopes for use in medical diagnostics and treatment from other countries. We don't have our own, high density production of these isotopes.
Is it Iran? Doesn't Iran say that that's one of the reasons they want the nuclear program?
Mm-hmm. Yeah, I think so.
This is the
And the thing about the type of breeder reactor that, say, India is trying to build, it uses an isotope called, it will eventually use an isotope, thorium-232, which turns into another isotope of uranium-233. And I'll go, uranium's most stable, or the most stable isotope of uranium is uranium-238. And in the Manhattan Project, what they did with uranium ore, which is 95% U-238, and other types of uranium, particularly uranium-235, which is the type of uranium that decays into the nuclear the nuclear fission. And so they had this very extensive process, very electrical consuming, time consuming process where they actually take the ore and they vaporize it into a gas. I think it's a type of uranium fluoride type gas. And then they separate out the uranium-235 from the 238. But this is a very difficult process. And the U-235, they eventually enrich this U-235 in order to use it for nuclear power or the nuclear bomb. And this is one of the things with some of these people claiming that these terrorists can build some of these nuclear bombs. The actual bomb itself, not the actual uranium, but the rest of the bomb, is what I call nothing fancier really than a potato gun. All it is an atom bomb is you have a type of uranium-235, like a block of it on one side of a tube, and you have another U-235 block on the other side, both of which by themselves are not fissible, meaning they would not self-destruct. But what happens is that on the one side you have an explosive that shoots the one U-235 block into the other, and that actually, now that these two things together combine into an explosion. That's how an atom bomb works. The actual machinery and the tube and the actual casing, you've all seen pictures of the bombs dropped on Hiroshima. That part of the bomb is not that difficult. I mean, you need the machine tools, you need that science, but that's the easy part. What's hard is the uranium-235 to enrich from the uranium-238 ore. But what Iran, and I think Iran is doing this, and I think what India is using, which is this thorium-232, you take that and I think you shoot neutrons into it and it transforms into uranium-233, which is only usable for nuclear power. It's not fissile. So there's no way, if you have a thorium plant like India is building, that you can make a nuclear bomb out of that. It's a different process. And I don't know what Iran is trying to use. I'm not sure. But that is one thing. This is how they used to make before nuclear reactors. This is something called a cyclotron. Some of you know Dr. Moon from the Fusion Energy Foundation. Some of you might have heard of the name. He built the second cyclotron in the world for the Manhattan Project. Moon was a collaborator of the Fusion Energy Foundation later on. I won't get into the physics of it, but essentially you have in the middle here, right in the middle is where you shoot these radioactive isotopes, a whole bunch of them, I think, different areas. And you have these two magnets, so like two Ds put together, put in a circle, and you have the radioactive isotopes go through, they shoot upwards, and then they eventually spiral out because of the magnets, and you can extract these radioactive isotopes. But it's a very slow and expensive process, and you don't really get that many isotopes, especially not for what we need nowadays.
Pardon me, wasn't it Ernest Lawrence that invented the first cyclotron?
Mm-hmm. Yes.
He was the original.
Yeah. But I was saying, Moon invented the second one. So, yeah. All right, this is another application of isotopes. and I'll get into exactly what I mean by this by the next one. Carbon dating. This is a cartoon. you know, carbon, the carbon that you find in a diamond or a pencil or a piece of coal, that carbon is called carbon-12. It has 6 protons and 6 neutrons. And that's the most abundant form of carbon. But you also have this radioactive carbon called carbon-14. I'll get that a little bit. And this is just an illustration of how it's formed. Cosmic radiation from the sun, neutrons bombard the nitrogen in the atmosphere, and it actually creates carbon-14. The nitrogen-14 goes into the carbon-14. And this is actually, and then the carbon-14 gets chemically bonded to form the CO2. But it's CO2 with a carbon-14 atom instead of the usual carbon-12 atom. And so this carbon dioxide, which is radioactive, gets absorbed into the plants. They use it for photosynthesis. They do actually separate it out. There are theories of how they know which is the carbon-14, which is the carbon-12, based on the weight or the spectral that I was showing you earlier. And so the plants and so forth intake the carbon-14. There's a certain ratio. I will say that the ratio in the atmosphere of this carbon-14 to carbon-12, it's a steady ratio. It's a constant ratio. And so the intake by the plants is also at a constant ratio. And so they're continuously intaking this radioactive carbon dioxide throughout their life. But of course, when they die and they eventually get buried, they don't take in the carbon dioxide anymore. And so within a rotten log or a wooden mummy or an axe from the Stone Age with a wooden handle, when the wood specifically died, it had a certain amount of carbon-14 and carbon-12. But because carbon-14 is radioactive, it decays over time. Something called the half-life. How much half of a radioactive isotope, take a sample of carbon-14, for instance, the amount of time for half of that sample to radio decay into the carbon-12 is about 5,730 years. And for the second, that remaining sample, for half of it decay, the carbon-12 is another 5,730 years, and so forth. So what this means is that, when the wood is first buried or first used by a primitive human, the radiation is at its maximum. The carbon-14 is the most it will ever be in that sample because the plant has stopped and taken the carbon dioxide. And so it radiates at about the 100%. But say in 5,700 or so years later, say you're looking at an old stone axe, you can measure that the radiation is only about 50%, because 50% of the carbon-14 decayed in the carbon-12. And similar processes, another 5,730 years, it's only about a quarter of what it originally was. And so you can look at any old wooden artifact and you can measure how much radiation is coming from the wood. And it's a very small amount, of course, but you can measure it. And for instance, if that mummy, which was wood, is showing that it's around 50% radioactive, the relationship of the carbon-14 is only about a half as it was, then you can guess that it's as old as 5,730 years, because it decays at a constant rate. And so you can actually investigate how old, up to about 50,000 years or so, how old some of these wood things, especially with carbon-14, but there's a whole bunch of other isotopes with stones and so forth of water that you can actually start to go back in time and see various things and so forth. That's what that was. Well, this is another cool one. Your smoke detector uses a special type of isotope, Americium-241. And I was actually gonna, I was gonna draw it actually. I don't have a picture of it. So you have, in a smoke detector, you have, you have sort of like a, you have a block of steel or lead, or not lead, but some sort of normal metal. And you have a small amount of Americium-241, which is a radioactive heavy metal. And that, it emits radiation. I think it emits beta radiation, which is high-speed electrons. So it emits this radiation. Okay. And so what they've done is that they've taken these two plates on the side, and just like the cathode ray tube that I was showing you before, and it's very similar to how this candle works, that you have a positive and a negative current flowing through it. And what happens is, in this area right here, that's the symbol for beta radiation. The oxygen and the nitrogen, the atmosphere, is ionized because of the radiation. And just like how you can test the flame actually conducts the electricity, there's a current that runs through this ionized area. And so there's a current going through there. What happens with you, in our office, the toaster doesn't work all that well. What happens if you have a couple of these big smoke particles? A couple of these very big smoke particles coming in and so forth, coming in the way. What happens is that these smoke particles aren't ionized. They're too big. They're really complex. And so this circuit that was formed because of the ionization is cut off because of these smoke particles. And so that it gets cut off, and then there's a signal going back to the beeper to go off. And that's how your smoke alarm works. And so that's a very, most people don't think about it, but fire detectors have saved many lives. Is another application of an isotope. I just wanted to go through that. That's that. Oh, this is just nuclear fission again. This is the U-235 I was telling you about. You throw a neutron at it, it splits, I guess U-236. There's a couple of different ways it splits up. It's not always the same way it splits up, but then it releases neutrons and energy. It's more isotopes. This is a thing from the 1950s, from the Hanford site. In a normal nuclear power plant, I think this is in Germany, that chain reaction, as Art was telling you about, if you control it with what we call heavy water, you can have a controlled nuclear fission reaction. You can heat up the water, and it turns into steam, and you can generate electricity from that, and it's controlled. And this is, of course, going back to the political. This was in the 1950s, the Atoms for Peace. The whole idea of using the discovered principles of isotopes for the benefit of mankind. define the way by which the inventiveness of man shall be concentrated to his life. This is the type of thinking that was going on back then, or at least generally, not by everyone. But and that's what happens if you have a chain reaction that's uncontrollable. We all know that picture. And this is nuclear fusion, which is deuterium and tritium forming together into helium, neutron, and energy. And controlled, this is what we have with, this is a tokamak. And then this is actually the jet tokamak. This is a picture of it. Let's see what else. And that's what happens when you uncontrol a fusion reaction. That's the first hydrogen bomb test. So, awesome. And an interesting thing is, I might have this. The sun is a lazy bum. It just sits there. It has a fat butt. Doesn't do much, mostly. But the interesting thing within the next picture, within the core of the sun, if you take a cubic meter, of the sun's core, it's very hot. It's tens of millions of degrees. It's very dense because of the giant compression of the entire sun into the core. But the actual net energy produced per cubic meter is less than what our body produces. The actual absolute number of the fusion reactions going on within a cubic meter of the sun is very, very low. Maybe even a couple per many, many years. It's not a lot of the actual net, but of course, this is per cubic meter, and the sun has about 1.5 times 10 to the 27th cubic meters. So you're talking about, per cubic meter, not that much, but the sun is really, really big. And so, and of course, our type of sun is a very slow burning star. It takes about 10 or so billion years for it to use up all of its fuel, which is the hydrogen. People know the red giants and the much larger stars, they only last a couple 100,000 years. They don't last as long as our sun, because within their core, the number of fusion reactions is much greater. They are much hotter, they are much bigger, but they use up their fuel really, really quickly, and they burn out, they supernova.
The faster they go.
Mm-hmm. And an interesting thing with trying to figure out fusion energy here, we have our work cut out for us. We don't have a giant sun to compress the atoms together, and we have to create many more fusion reactions per cubic meter, so forth, than the sun does. Many millions or billions of times more cubic reactions. And we have to not have it explode in terms of a nuclear fusion bomb. But one thing that's very interesting, this is a spheromac, I believe. This is not a tokamak, which is the donut shape. This is a spheromac. And what I believe it's trying to do, and I don't know the full physics, is that very, very, very hot plasma. People know plasma, generally you can think of it as ionized gas, the electrons and protons flying around, very, very hot and so forth. But when you get to 100, 200, 500 million degrees, the normal ways that people think of these ions and plasma don't really, they don't apply anymore. And what's been discovered over the years is that plasma sort of has its own, it's not chaotic at a certain point. It is chaotic on the small scale, but it actually forms various different shapes and geometries. The spheromac is actually to allow the plasma to sort of form its own shape, its own geometry, its own natural geometry. So that once it actually forms its own geometry, then you can actually try to get it to fuse, I would say, using energy flux density. You have, once it's in its own geometry, then you're not just applying heat to every part of it. You're applying heat to a very small part of it. And so then it actually forms this. This is very interesting. I guess we didn't show the video, but
I don't know if we have time, right?
no, that's fine.
20.
Okay. One application of fusion energy. Some of you saw the video last week, but if you take the very hot plasma from the fusion tokamak or spheromak or whatever, and you ship it down in a tube, one of the things you can do with relating to isotopes, this hot plasma has a whole bunch of these isotopes vaporized and so forth in the plasma. You can separate out whatever isotope you want. There's an actual name for it. Yeah, plasma separation process. Okay, it's not that fancy. But what you can do that and if you remember the chart that Art was showing with the Westinghouse, and the spectral lines that I was showing before, every isotope has its own specific radiation frequency, its own sort of light, so you can call it. If you have a magnet tuned, a very strong magnet tuned to a very specific frequency, and you target it through the plasma, you sort of like a microwave with water molecules, they vibrate and they heat up. You can energize whatever isotope you want and take it out of the plasma, and you can collect it and so forth. The video shows through it much better. This means you can actually mass produce these isotopes for medical stuff or for alloys, different metals and so forth. Advanced stuff for the robotic systems that we would have on Mars or Venus. Metals that could have much higher densities, much higher melting points, or lower melting, or higher melting points. Because the different isotopes have different properties. And that's just one example. Different geometries. This is a buckyball of beryllium, I think beryllium. And beryllium-7, I think is what they use, normally is a very radioactive, or it's a radioactive isotope. And it decays rather quickly by itself if you just have one of it. However, if you create this buckyball out of beryllium, its radioactive decay is much shorter. It doesn't decay as fast. And I don't know exactly how it works, but there is some hypotheses about the geometries of some of these different isotopes. And this is, of course, most of you know Vernadsky talks about the biosphere, and then the noosphere and the geosphere. Now these are different geometries. You have your normal Earth geometries, and life has its own geometry, and human beings and human culture have their own geometry as well. And so, a whole bunch of these seemingly radioactive isotopes by themselves, if they were just out in the nature, would instantly decay. But, various processes with life or with magnets or with different shapes like this, were discovered that some of these isotopes behave much differently in different, fields, magnetic or so forth. And so this is a whole branch of trying to understand, pretty much confirming what Vernadsky was hypothesizing. This is Mars. To go to the point that life in the plants, the plants taking carbon dioxide, the carbon-14 differently than the carbon-12. There's a sort of relationship of a whole bunch of hundreds of these isotopes here on Earth that plants, animals, we use But on Mars, those concentrations are different. You know, for instance, I think potassium within the body, which is used for bones and so forth, some of it's radioactive, but the relationships, or the ratios, the actual amounts of potassium on Mars are much different. So if you're trying to, if we were eventually in a couple of years to actually human colonize and terraform the planet, we would have to discover, where there are different isotopes there. Perhaps because of Mars' weakened magnetic field, that some of these isotopes aren't intaked into the body as well. And I think NASA is about to, I don't know if they launched the MAVEN mission, they did, okay. That the MAVEN spacecraft in a couple of years will get to the Mars, and it'll study its atmosphere and actually search for some of these isotopes, how much there are, what other types there are.
Next September.
And just to bring it back, once we understand that there's this whole other degree of freedom, you have these 115 elements, but now you have over 3,000 isotopes. Now that we understood what the isotopes were, there's another degree of freedom with how we can, understand things. And that's the whole point of, what makes man different than animals, is that, the ability to understand, different processes. There are no limits. Okay, well, I guess that's it. So, all right.
Q&A?
I have one question about, you said that 1 square meter in the core of the sun was much hotter than on the surface. Or
The core of the sun is
less hot.
about 50 million degrees. The actual surface, like there's an actual surface to the sun. It's only like a couple thousand degrees, maybe like 10,000 degrees.
So what's the explanation? You would think that something so hot would give off more energy, because heat is energy, one form of energy. So why is it so minimal, 1 square meter?
Well,
of degrees? Is there an
I mean,
explanation?
one thing is that I guess an atom is mostly empty space, and so you have the fusion is the nucleus of the hydrogen coming together, but most of the atom is empty space, and you have the nucleuses together, which are both positively charged, and they repel each other. So you have to have these very high temperatures, but even with those temperatures in our sun especially, 50 million degrees, it's hot enough and dense enough to have these few reactions. It's hot anyway, there's heat there, it's not a lot of energy, but the net energy put off, which is the light coming from the sun, the radiation and so forth, that's in the core of the sun. It's not as much as we think, but of course the core of the sun is really, really big, so overall it does produce a lot of energy. So, and I didn't bring it up all that much. It's sort of a off topic, I guess, but well, I don't know.
Go ahead.
Is it okay?
You showed a slide of a buckyball on the periodic table of elements. Where's that? And
That buckyball was, well, I don't know if that buckyball was beryllium, but a buckyball made out of beryllium has this interesting feature that its half-life is elongated, meaning that it does not decay as fast. The beryllium in the buckyball does not decay as fast as the beryllium just a whole bunch of beryllium atoms. So there's some geometry of the buckyball that affects the nucleus of the beryllium that makes it that it doesn't, and some of you might know Dr. Moon. his theory of the nucleus is that it's platonic solids, nested platonic solids. The protons and the neutrons are geometrically arranged. And so maybe the buckyball has some sort of relationship to the nucleus, I don't know. So, any other questions?
Aren't the protons made up of quarks? Like a proton would have 2 up quarks and 1 down, and each quark has a fraction of electrical charge.
Yeah, I mean, that's a theory, yeah. So,
But the electron is not made up of any quarks. It has no substructure, as far as we know.
well, I mean, some of the modern quantum physics, you have to wonder, but I don't know that question, so.
Well, just one comment, because that thing about the decay of isotopes taking longer in different geometry, that must be a new discovery. I don't remember.
Well, Vernadsky had hypothesized, and I think it's actually been a couple of these elements within live-in processes, some of these isotopes. They're a way like the plant actually distinguishes between carbon-14 and carbon-12, for example, the similar stuff of oxygen and nitrogen, that there is the way that the plant does it is not always by weight. You can separate, these atoms by weight, but some of these processes, and I don't know the full scope of it, but somehow the plant knows that the different geometries of the different isotopes.
And so it's the ones it wants.
Yeah.
Okay, all right?
Yeah.
All right.
Okay.
Great work.